Welcome you all in this 15th lecture on metric spaces, and where we will discuss several MCQs related to the metric spaces, okay, open set, closed set, diameter, and so on and so forth. Or you can say whatever we have studied so far, we will see some MCQs. So we will continue. In the previous talk, we have also seen several MCQs, and now we will continue this one. So here is, I have another MCQ which says that let X be a metric space, A and B be non-empty subset of X, and rho AB denote the distance between A and B, then which of the following statement is not correct? Okay, which of the following statement is not correct? Now here is rho xb is equal to 0. Okay, we have seen that rho xb is equal to 0 does not imply x belongs to A. This we have seen in a remark. Okay, we have also seen that rho ab is equal to 0. Then it does not imply that A and B have common point. Yes, this you can see that this is equal to 0 then does not imply. So this is this is equal to 0. This does not imply that x belongs to this. Yes, this is correct statement, and this is also a correct statement. And if D is a discrete metric, then A and B are bounded. Okay, okay, because with respect to any, they are bounded. But if rho xb is equal to 0, then x belongs to B. Okay? No, this is not true. X, we have proved that if this is equal to 0, then x belongs to the closure of B. Okay? So this statement is not true. The rest of the statements are true. Okay? Similarly, let's take some other. We have already proved that if A, B are two non-empty subset of a metric space X, and rho AB is the distance, delta A is the diameter of A, then which of the following statement is not true? Okay, now we have proved that the diameter of A is equal to 0 if and only if it is a singleton set. This I have already given you. I have already given you that the diameter of A, the distance between A and B is always less than or equal to dxy for all x is in A and y is in B. We have already proved that if A is a subset of B, then the diameter of A is a subset of the diameter of B. So this we have already proved, but we have not proved this one. Okay, so this is a not true statement, because the rest of the statement are true, so this should not be true. If this is true, then none of the true, which is not the correct answer. Okay, then you see that again here which of the following statement is not true? The diameter of A union B is less than or equal to the distance between A and B. Okay, so this statement, this we have proved, this we have proved, this we have proved. So all B, C, D we have proved, but we did not prove, we have not proved the part A. So this means that the statement A is not true. Now let's come to the spheres. So X be a non-empty subset with respect to the discrete metric. Okay, with respect to the discrete metric, then the open sphere. So you remember that I have considered if X is your discrete metric, then the open ball with center at X and radius R is the singleton set if R is greater than 0 or less than or equal to 1, and it is equal to whole space if R is greater than 0. So the answer is this thing, and rest of the things just are not correct. So you have to remember that, or you have to verify. You can verify very easily, because this is the set of all dxy. In the discrete metric, you see that d dxy is equal to 0 if x is equal to y, is 1 if x not equal to y. So this is the metric. And now what is your SRx naught? SRx naught is the set of all points y in x such that dxy is less than r. Now you can see here is so if you will see here is then what you will get if r greater than 1. So r is greater than 1 because this is always this is always 0 or 1. Okay, so it means that this 0 or 1. So if it is greater than 1, if this is greater than any number greater than 1, then it is true for every y. So it is whole space. And if r is 1, okay, then this is 1. So this is true only when the y is equal to x or y is equal to x naught. You can see here is so this is your x naught. So y is equal to x naught. So you will get this point. Okay, so you will get this point. So this is the way you can see that the interior the ball in the so the answer is here. So you must remember that similarly for the closed interval, closed sphere or closed ball, the answer is this one. This we have already mentioned. So sometimes you remember, sometimes they are no need to verify all these things. Now we have seen that also when x is this is your metric space with the usual metric, then the open ball with center at origin and radius is center at 0 and radius is r, then the answer is we have mentioned that the answer is this one, and you can also check the answer is this one. Okay, similarly you can see that the closed ball is the answer is this one. Okay, so here is we have now here is look here this is a very important question. Now let x be a metric space and d defined as dxy is equal to 100 if x is not equal to y and it is equal to 0 if x is equal to y. It means what? It means that it is similar to the discrete metric. In the discrete metric, dxy is equal to 1. But here, what I am writing, dxy is equal to 100. The rest is okay. So if it is 1, so as we have seen that the open ball with center at x naught and radius r is equal to the singleton set if r is greater than 1 and less than or equal to 1 if it is a discrete metric. Here it is 1. If it is 100, so it is less than or equal to 100. And it is the whole space if r is greater than 100. So this way you can see that you can check very easily. Okay, no need to calculate the everything. Okay, if you remember, then you can do it very fast. Okay, let's take another example. Here is for the same thing for the closed ball. So for the closed ball, you can do the same in the same way. So the answer would be this one. So now here is this is important exercise. So let x d be a discrete metric space. Now we keep in mind discrete metric space. Okay, and you have the ball with center at x and radius r, and here you have the ball with center at y and radius s for some xy and some positive number n, and the balls are same. Okay, then can we say that then which of the following is true? X is equal to y, rs must be less than or equal to 1, rx must be greater than 1, ix is not equal to this but x is equal to y. Okay, so it means what? It means that you see that these balls, whatever is r, okay, so rs is less than 1. If rs is less than 1, then the ball in the discrete metric space is consisting the origin. So this is your x. Okay, if Rs is less than or equal to 1, then this is equal to x. And this is equal to y because s is less than 1. So x is not equal to y. But here is x is not equal to, so this is not true. Okay, so this will get x is equal to y. But if r is greater than 1, then this is equal to whole space. And whatever is your x. Okay, so but r is greater than 1, then this is your whole space. Similarly, if s is greater than 1, then this is the whole space. So if r is greater than 1 and s is greater than 1, then x, this is your x, this is your x. So those both are true. It means that this C is correct answer. So this way you can see that C is a correct answer. Now we have another question here is, look here is, this is let A, B, C be non-empty subset of a metric space X. The negation of the following statement. What would be the negation of this statement? That for every epsilon greater than 1, there exists A, small a in capital A, small b in capital B, such that for all C in C, DAC is less than epsilon and DBC is greater than epsilon. So what would be the negation of this one? So negation means that, means what? Negation is for every. So for every means there exists. Okay. So for every means there exists. There exists means for all. Okay. So negation of this, there exists for all. Okay, and also for all there exists. This is less than means greater than or equal to, and this is greater than is less than or equal to. So the negation of this would be there exists epsilon is greater than 1 such that for all A in A, B in B, there exists C in capital C such that DAC is greater than or equal to epsilon, or the negation of this here is and, so here is or DBC is less than or equal to epsilon. So it means that the statement D is correct. So one must know what would be the negation of this statement. Now let us see, here is one more. Let A be a non-empty subset of a metric space X. Then which of the following statements is true? A point X is an interior point of A if it is the center of every open sphere contained in A. No, the definition was that a point X in A is an interior point of A if it is the center of some open sphere contained in A. Okay, so you keep in your mind, if a point X is the interior point of A, if it is the center of some open sphere contained in A. So the statement B is true. Okay, every point of the set A is always an interior point of A. No. A non-empty, an interior point of A may not be a point of A. No. Interior point must be a point of A. Now, let A be a non-empty subset of metric. Which of the following statement is not true? Now you see here which of the statement is not true. So here is let A, if the set A is open, if each of its point is the center of some open sphere contained entirely in A. Okay. A is open if and only if each of its point is an interior point. A is open if some of its points are the centers of some open sphere contained entirely in A. Every open set is the neighborhood of each of its points. So here is which of the statement is not true. So which statement is not true? That the set A is open if sum of its points. No. If the sum of its points are the center of some open sphere contained entirely in A. No. It is not true. The A is open if every point of it is the center of some open sphere contained in A. So this C is not true. Okay? Then see here is this I have already mentioned this as an a remark or as an example that if A is your set of natural numbers, integers or rational numbers or irrational numbers, then the interior of A is your empty set. Okay, if A is set of natural numbers or set of integers, but not this, then the interior of this. No, these are not correct, but this statement is true, which we have already seen. So this I just you can make the examples by yourself. Okay, this I have already given. This also given in your exercise in the remark that if A is your finite set, the interior of A is empty. So this statement is true. Okay, this here you can take a minus. So this should be closed interval. The interior of this is this no, this is true. This interior of this is empty. This is not true. Finite set, if A is finite set, the interior may be, this statement is not true. The interior of this is okay. The set this is not open. Yes, this is not open. This is correct, but this is not correct. This we have already seen that this is true, but this is not true. I have already given you the exercises. So this is, and this 30 question number 38, we have seen that which of the following is not true. Now, look here is this statement, which we have the following statement. In the discrete metric space, every subset of X is an open set. Yes, it is true. Because every subset of a discrete metric space is open as well as closed. So the statement A is true. Okay, and then you go from here. So either this is true or this is true. Forget about these two things. They 100 not. So only you have to check C and D. Forget about the B. In discrete metric set X cannot be open. So this you forget about this one. Now the open, this is your real line in R2 is not open subset of R2. Okay, this is not open subset of R2. This is correct. And this, the X is this in R2 is no, this is not correct, but this is correct. So A and C. So A and C. So this is true. So this way we can prove that this is true. Okay. Then we have several others. So if A is a subset of the closed interval AB with non-empty interior, and let Q plus A is equal to Q plus A such that this is equal to this one. Okay, which of the following is true? Q plus A is equal to R. Q plus A is equal to Q. Q plus A need not be closed in R. Q plus A need not be open in R. So the answer is your A. Now we have for this draft set. So this I have already given. Same as here you have which of the following statement is true. We say a point is a limit point of A if each open sphere center at X contains at least one point of A other than X. So this is true. Okay, of course the rest would not be true. Then here is you have A, let A be a non-empty subset of metric space. Which of the following statement is true? A point X is an isolated point of A if this is equal to X. Okay, for every R, this is equal to X. for some r, this is not equal to singleton set. If for some r is greater than 0, this is not equal to for every r. So, but we have mentioned that if by the definition, if point x is an isolated point of A, if the open ball with center at x, and if there exists r greater than 0 such that SRX intersection A contains only that point, then that is so. This is the definition of an isolated point. So B is true. Okay, so this I have already given. Okay, now here is keep in mind, I have mentioned that the closure of an open ball is not equal to the closed ball. So this is not true. Okay, so which statement is not true? So this statement is not true. Forget about all the others. Okay, this we have already mentioned in the remark, so I am not going to come this one. And then here is the definition of the boundary point. So you can see the boundary point, and then you can see here is look, here is the important thing is that consider this is your set of all rational numbers with the usual metric. Okay, and if suppose this is true, then it means what? It means that x is less than or equal to under root 2. But under root 2 is what? Is your irrational number. Okay, under root 2 is your irrational number. So, and here is so here is this, and then you have B is your mod of this is less than 1, x square is less than 1, and under root x is less than 1. So A and B are open but not closed. They are open but not closed. Okay, so the A statement is true. They are open but not closed. So it's simple one. So this you can define. This I have already given you in the exercises. I am not going to repeat all these things. So this is about the closure, interior. So this again I am not going to repeat. This is also, I am not going to repeat all these things. This I have already given you again in the exercises. So you can see here is for the subspaces. So x we metric space with the then the following step. If y is equal to this, then the set this is open in y. Look here is this is open in y. Yes, this is open in y but not in R. This is correct. And if this is equal to, then this is closed. This is not closed. This is, but here is in this set is closed. This set is closed. Okay, so this is closed and this is open. So A and C are correct. So A and C are correct. So B is correct. So B is correct answer. So you can see here is again this is what subspace. Then consider the following statement. A is open in Y, may not be open in X. Yes. A set closed in Y may not be closed in X. A is open in Y if and only if there exists an open set G in X such that this is true. Okay. A is closed in Y if and only if there exists a closed set F in X such that this is true. So C and D are true. Okay. C and D are true, and this A set open in Y may not be open. This is true. A set closed in Y may not be closed. So all our statements are true. So all A, B, C, D are correct. So D statement is okay. Okay, so these are the exercises. These are the MCQs related to the chapter 1 which we have considered so far. Okay, and now I stop over here. and we will discuss in the next talk. We will discuss some other. We will discuss in the next talk. We will discuss the complete metric spaces. Okay, so thank you very much. I stop over here.